When we're working with matrices, a lot of times we want to figure out how to strategically manipulate a matrix. So perhaps I have this matrix, one of my favorites because it's the simplest, 1, 2, 3, 4, and maybe we want to transform it in some specific way, as we can do with vectors. We're going to define something called an elementary matrix. And as the name suggests, it's the most basic matrix that performs what we would consider one of the most basic operations. So an elementary matrix is the identity matrix with exactly one of the 3 row operations performed on it, with a row scaled by a non-zero constant, 2 with 2 rows switched, or 3 with a multiple of 1 row added to another. So we know that the identity, if I were to write I2, or you could put I2 by 2, but I2 is sufficient, it would be 1, 0, 0, 1. And what we know that the effect that this will have on any matrix doesn't matter what you multiply it by, or in what order you multiply them by for that matter, you're going to get the exact same matrix back. So we can see that what will end up happening is we'll be scaling the first row by 1 and the second row by 1. So that's the way we could think about this. Now, let's suppose that we define E to be this matrix K0, 0, 1, and we want to know what effect will this have on the product AE. So notice that what's different here about the identity is that I could think about this as K times row 1 of the identity. Okay? K times row 1, it basically means that we multiplied 1 by K and we multiplied 0 by K. And so that gives us the row K0. So let's see what impact that has and help us better understand why this is called an elementary matrix. So if I take A times E, what we know about matrix multiplication is that K will scale the first column, 0 will scale the second, and we'll get the sum of those, K times 1, 3, plus 0 times 2, 4, giving us the product, that's just the first column. Now we need to move on to the second column, and now we'll have 0 times 1, 3, plus 1 times 2, 4. Okay, now this is going to give us, here we'll just get only a result from this first vector because the second one's being multiplied by 0, and that here is key that we have these 2 zeros here. And that's going to give us 1k and 3k. And in the second column, we'll get the vector 2, 4. Now notice what effect this had. This effectively scaled the first column of matrix A by k. All right, so we took K times column 1. And that's what operation that performed, as we see here, by taking the identity matrix and scaling the first row of it. Now that's what AE gives us, but what will EA give us? EA is the multiplication in the opposite order. So let's go ahead and execute that. So the difference will just be, we'll have K0, 0, 1 times 1, 2, 3, 4. And now in this case, K0 and 0, 1 are being scaled by 1 and 3. So this will give me 1 times K0, 1 times K0, plus 3 times 0, 1. And then for the second column, 2 times K0, plus 4 times 0, 1. And so notice what effectively is happening here. 1 and 3 were the elements of the column here, 1 and 3, and 2 and 4 were the elements of the column here. Now in the first case, we see that 1 is getting scaled by k, but 3 is multiplying 1, and so that's just going to give us 1k and 3, and this will give us 2k and 4. So the effect here is different, but kind of has the same idea. This order of taking EA, it took K times row 1. So if our goal is to multiply our matrix by a row. Now remember, we can't, if we scale a matrix, we do like k times a, that's going to scale all 4 components because of the way scalar multiplication is defined on matrices. But by creating the second matrix, this elementary matrix that just has the multiplier, or that we multiply either a row 1 or row 2 by that constant, that in effect will then transfer onto the matrix that it multiplies. If we wanted to multiply row 2 by k, then we could make this 1, 0, 0, k. Now, what effect will this have? Notice that here all that's happened is the rows have been switched. And what I mean by that is relative to the identity matrix, the rows have just been interchanged. That's all that's taken place. So if we now take AE, so we'll take 1, 2, 3, 4 times 0, 1, 1, 0. So I think, based on what I'm observing up here, my hypothesis would be that, well, if multiplying the row of the identity matrix by a constant and then multiplying it by a matrix scales the column by that same k, then I think that switching the rows here in this order, AE, will switch the columns. It will switch the columns. Let's find out. So we'll have 0 and 1 scaling the 2 columns, 1, 3, and plus 1 times 1, 4, 2, 4, excuse me. You can already see that this first column is going to be 2, 4, which was the second column in the first matrix. And then we'll have 1 times 1, 3, plus 0 times 2, 4, and that's going to return 2, 4, and 1, 3. So we noticed that we had columns switched. Column 1 and column 2 were just interchanged there. Okay, so if I do EA, and I'm going to skip some of the multiplication here because we can probably guess what this is going to do. If you do the elementary times A, that's going to operate on the rows. So this is going to affect columns, and if your elementary matrix multiplies from the front, it's going to affect the rows in whatever way you have changed that identity matrix. So if we do E times A, it's going to switch the rows of our original A matrix. So instead of 1, 2, 3, 4, this will be 3, 4, 1, and 2. So this will switch row 1 and row 2. Well, they'll get interchanged. That's kind of cool. Now let's take a look at this third case, and this is our third row operation, a multiple of one row added to another. So if you compare this to the identity matrix, 1, 0, 0, 1, notice that this matrix right here is 2 times the first row added to the second row. So 2 times 1 is 2 plus 0 is 2. 2 times 0 plus 1 is 1. So literally this is 2 times row 1 of the identity added to row 2 of the identity. We're only going to focus on, and usually we want to do row operations and not column operations. So typically we're only interested in EA, but I thought it would be interesting to look at it both ways. We're not going to focus on AE here because I think it gets a little convoluted with this third operation, so we're going to skip that. To do EA, we'll take 1, 0, 2, 1, and we'll multiply it by our A matrix, 1, 2, 3, 4. Okay, so in this first addition here, we'll have 1 times 1, 2, plus 3 times 0, 1. And in the second column, we'll have 2 times 1, 2, plus 4 times 0, 1. Okay, so the first thing that we should probably point out is that this is not obvious what's going on exactly, at least not at the moment, until we kind of, instead of using 2, we use the element k. Okay, I'm going to come back to that in a moment. This, for now, will get get us 1 plus 0 is 1, 2 plus 3 is 5, and then 2 times 1 plus 0 is 2, and 2 times 2 plus 4 is 8. Now, if I look at the original A matrix, which is this one, I see that the things that they have in common, and they have still have the same first row. But the second row has changed. And it has changed in a way that might not entirely be obvious. It became 3 turned into a 5, 4 turned into an 8. Well, let's think about what we did here. We took 2 times row 1 and added it to row 2. So if I took in this matrix 2 times 1 and added it to 3, I would get 5. And if I took 2 times 2, that's 4 plus 4 is 8. So you can remove the 2 in here and put in a k and see that this is really what's happening here. But what this did is it took 2 times row 1 of A and added it to row 2. So whatever you do to the identity matrix, one of these 3 row operations, if you then multiply it by A, it's going to transfer that operation on to the matrix A, which is pretty neat. Now, let's see if we can apply these principles. Let's say that what we want to do is find the 3 by 3 elementary matrix so that we add 5 times row 1 to row 2. So here's how we start. Since we now know that E times A where E is an elementary matrix, one of the 3, we'll then transfer that operation onto A. What I'm going to start with is I3. So the identity matrix that is 3 by 3. It's going to look like this. Now, to form E, what I need to do is I need to take 5 times row 1 and add it to row 2. So let's think about what this would look like if I took 5 times this row right here and added it to row 2 without changing the first row. We want to keep the first row the same. We take 5 times 1 plus 0 is 5. 5 times 0 plus 1 is still 1. 5 times 0 plus 0 is 0. And so now, if we multiplied this matrix, E, by any 3 by 3 matrix, it would take 5 times row 1 of that matrix and add it to row 2. So if I define, A to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and now I carried out this product with E, what I would get is 5 times row 1 being added to row 2. So you can carry this out. You'll see that 5 times 1 plus 4 is 9. 5 times 2 plus 5 is 15. 5 times 3 plus 6 is 21. And then we get 7, 8, 9. So by just changing the elementary matrix and by one of these row operations, you will then pass on that information to the next matrix, which is just super interesting and powerful.